All right.
Put it all in there.
Yeah, it's like 90 degrees.
Do it inside of the sauna. Where did they do it? What room's got 90-degree capabilities?
Like, it's called the front desk.
What room has 90-degree capabilities?
He's gonna make a corner joke. He's gonna make a corner joke.
I mean, like, there's.
This guy.
Hey, there's this one too, right? What?
All the rooms got 90-degree capabilities, dude.
90
degree Fahrenheit?
Hold on, watch. I think this room has 360 degrees, because watch. Good one.
Oh, Dr. Mike.
I could have tried to do a cartwheel, but I'm not doing a cartwheel.
You know what? I want to see it.
You're going to have to learn to live with the disappointment.
Well, I've been disappointed for a long time.
He's like, every time I come to this class,
We didn't choose this profession to be not disappointed.
All right, so let's get started. I'm still working on the exam, but I put up here the statistics of the exam so far. So I've only got one problem left to grade out of the 4 that's on the exam. And in the end, I think everybody did pretty well. So so far I'm tickled with everybody's performance. What I can tell you that I'm just like skimming through the one that I have left to grade. Really, if there's any errors, they're not conceptual errors more than they are bookkeeping errors, which aren't big. That's not a big deal, right? Those are little things. That doesn't mean there won't be deductions, but I don't think it's gonna. Just me skimming it, I don't think it's gonna be like a 40% average. Like I don't think that's gonna happen. So in the end, like I've been teaching this class for a while, and I see a crop of exams of students that I think are doing very well. So so far I'm tickled. Today what we're going to do is we're going to continue our discussion of bolted connections. I'm going to try and make it a little more real today. And you'll see what I mean when we start getting into this. First off, let's just sort of recap the math. I want to make sure that everybody understood what we did in class and what we did on the last homework assignment. And my apologies for pulling a sneaky on you about the thread condition. But I didn't tell you what the thread condition was. I made you use your noggin. If you do not know the thread condition, what do you do?
Assume.
Assume what?
Worst case scenario.
And what is the worst case scenario?
That the threads are excluded.
You say that, you have that little smile on your face. You know. You assume the threads are included. The threads being included would be the worst case scenario for bolt shear capacity. Yes, sir.
I just wanted to say, like, my favorite thing about this class, or just this in general, is like there's a lot of fail-safes included. So it's like if you don't know, pick the worst case scenario, and then something else like, well, we're not sure worst case scenarios, and then by the end of it, it's like it might be overbuilt, but that's not a bad thing.
You know, so it's funny you say that. There are there is a philosophy in connection design, which we will talk about later, which is called designing to develop a full capacity. So let's just sort of fast forward a little bit and talk about connection design, because here's how connection design works if you want to have a nutshell approach to it. So what you do is, if I tell you to design a connection, the first thing you need to do is you need to determine the factored load, right? So you have your dead load, your live load, your 1.2 deads plus 1.6 live, and you get, 200 kips, right? Okay, now let's say you are designing with A325 3/4 inch diameter bolts, whatever. You look at the shear capacity of a single bolt, right? And you get a number, 17.9, whatever the number is. And so you have 200 kips on the entire connection, and each bolt can withstand 17.9 kips. How many bolts do you use? You just divide, right? You just divide to get the number of bolts. You lay them out in a pattern that makes sense, that corresponds to both spacing and edge distance requirements. You check bolt bearing. Done. That's bolted connection design in a nutshell, and we're going to do that later, okay? But I want to talk about a little bit about the checks and balances, and particularly about step 1, okay? So the first step in a connection design is to determine the factored load that you are designing the connection for. What if you don't have a load? What do you design the connection for? Well, one of the things that you can do is design a connection to do what's called develop the full capacity. And what that means is that instead of using a load, instead of using a dead load and a live load, you take the member and you say, let's compute its gross section yielding capacity. Let's compute its net section fracture capacity. And let's actually use that number as the load, right? So the idea is that whatever connection you design, it doesn't need to be stronger than that, right? Because if the member is going to fail before the connection does, right? That's designing to develop the full capacity. So you actually have your structure, and it doesn't really matter what the loads are on the structure because you've already got your member selection. So that is actually a cogent theory that's used. Honestly, I think that's fine for initial design, and then you can start to tweak as necessary, but we'll get to some of those discussions a little later. Now here's our layout requirements. Again, we have minimum and maximums that we're checking, but if we're designing, maybe we'll use preferred, maybe we'll use minimum. I'll make sure you know on an assignment because I don't want to get 60 different answers and they're all right. So I'll make sure we know what we're doing. Everything can be computed except for minimum edge distances, because that just comes from fabricator preference, and that's why it's a lookup. Okay. All right. I like the real world, so I would like to discuss some of the things that we've been talking about and provide some real world context. Does anybody recognize these pictures that I took? That should be a hint. No.
Engineering lab.
That's the engineering lab. That's the building right over here, right? So one of the cool things about this building, my office was in this building when I first became a faculty at Marshall a long time ago. And I remember walking into the building and saying, ooh, I could see the steel frame. This is awesome. So I took some pictures here because I kind of wanted to work through a real bolted connection. And so I picked a connection here in the building, particularly the connections on this beam, right? So if we look at the structure, okay, so we have these round HSS columns that are supporting the gravity load. Between the two is a W shape, a W section beam, okay? These roof joists are framing into the beam, okay? All right, and that beam is connected to the column goes to the ground. So if we go back to what we did last semester in the wonderful world of structural analysis, let's go through this. I'm going to put this right here, we'll say real connection discussion. So let's take this picture here, put this here. Kidding me. Let's use the snipping tool. It doesn't like it for some reason. Sometimes the snipping tool, it likes that. Yeah, for some reason it doesn't like me to snip images, but when I use the snipping tool, it likes it. I don't understand. Okay. So let's go back to the wonderful world of structural analysis. So the first thing that we would do is we would treat these roof joists as beams, right? So the joists, right? So the joists would be something like this, right? We'd have a support condition, and we'd have a distributed load on the roof, right? Some distributed load. And how do we get that distributed load for these joists? And by the joists, when I say joists, I'm talking about these open truss looking things. Those are called open web joists. They're basically just roof beams, essentially. So how do I get the load per beam? Well, what I do is if I'm looking at, let's say, this beam, I take half this way, and I have the tributary area. Y'all remember that? Remember that from CE 312, Wonderful World of Structural Analysis? All right. So what happens is I get reactions, we'll call it RB for the beam reaction. Those are the forces that the beam has to supply to keep the joist upright, correct? Okay. So then, if I look at the girder, right, the girder in this case is the W shape. So let's see, so I've got the beam, I don't know, it looks like this. And how many do we have? We've got 1, 2, 3, I think 4, based on the image. I think that's 4. So you probably have something like 1, 2, oh, that's off, that scales off. So 2, 3, 4, right? Okay, now, let's see if y'all are paying attention. Is that RB? Is this RB? Breaking my heart. It's 2 RB. Because there's a beam here, but there's also a beam here, right? Right? On the girder, right, there's an open web joist framing this way and an open web joist framing this way, right? Because remember when we would have floor plans, right? Remember we would have something like, here's a column, 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 column. We'd have beams in between, or we'd have elements like this in between them. And then we'd have floor beams, right? Floor beams, floor beams, floor beams. And so if we were looking at that, this girder right here, if we were looking at this girder, it would have a support, support, and then it would have, I don't know, 3-point loads. But the amount of load that would come here would be 2 times the reactions. Because there'd be a reaction from this side and a reaction from that side. Y'all remember that? So what we can then do is we can analyze both the joists and the girder. And this is stuff we're going to do later in the class, is how do we design the beams to resist the moment, the shear, the deflection, etc. We'll do that near the end of the semester, right? But ultimately, what we're interested in is getting the reaction on the girder, right? That's supposed to be a G, not a B. Does that make sense? Okay, so now what I want to focus on then is the bolted connection. Okay, so let's take a look at that. All right, so here's kind of what we've got going on. So we'll say bolted connection. All right, so let's see. We've got a round column. So here's our round column. It looks like we've got a little plate sticking out of that. But we've got our I-beam that frames in. And then we've got a plate that sticks out. And so the plate goes back here, and then we've got something like 1, 2, 3, 4 bolts. Is that right? Does that look kind of right? Everybody with me on that? Okay. So we're getting, at the end of this, on this connection, we're getting this girder reaction, right? And let's just say, for the sake of discussion, it's 30 kips. It doesn't really matter what it is, but let's just say it's 30 kips, okay? So now we need to start evaluating this, okay? So let's look at this from a bolt shear perspective, okay? Okay, so for bolt shear, let me ask you this. Are these bolts in single shear or are they in double shear? I can zoom in if needed.
Double.
Is it double? Well, for it to be double, wouldn't there have to be a plate in front and behind? Like if here's the I-beam, like in other words, like if I looked at the I-beam or the W shape like this, so this is the girder.
So is that plate just welded to the round HSS?
Yes, we're gonna get to that here in a second, but you are right. There's a weld like right here.
Okay, so then it'd just be a single shear.
Yeah, there's only one plate, right? Because here's the plate, right? And the bolts are going through like this, right? So the bolts are only experiencing that single shear plane, right? So these bolts are in single shear, right? So they're single shear. There's 4 of them, right? And so if I told you they were A490 7/8" diameter bolts, all you would need to do is look up the capacity, multiply by 4. There you go. Make sense? Okay. Now bolt bearing. What about bolt bearing? Okay. Well, for bolt bearing, we have 2 different cases to consider. We have the case for the I-beam and the case for the plate. Let's just take the I-beam as an example, or the W shape. So bolt bearing for the W shape. So if I draw this a little bit more detail oriented, okay, so here's 4 bolts, right? Now, if you've got load on top of the beam, which way is this plate going to get mashed up on? It's going to get mashed up right here, isn't it? Right? Because you're standing on the beam and the bolts are keeping it up, right? So the bolts are pushing this way, right? So in other words, this is your edge bolt, and these are your interior bolts, right? Now, for your interior bolts, the capacity is the minimum of 1.2 LCT FU and 2.4 dBT FU, right? Okay? And in this case, I propose that LC is that distance, right? The clear distance from edge of bolt and edge of bolt. So in other words, this is how much material we'd have to tear through to fail the connection in bolt bearing. Does that make sense? Now, let me ask you this. Do you think that bolt right here is going to rip through this web and all of that flange up top? You really think that's going to happen? I don't, right? So probably what I would do for this edge bolt is I would just take the capacity as, I would just say based on the connection schematic, I know that edge bolt is just going to be 2.4 dBTFU. And just say, here's the capacity of the edge bolt, here's the capacity of the interior bolt, under bolt bearing, 1 edge bolt, 3 interior bolts. There you go. Does that make sense? All right, any questions on that? All right. Now, the other thing is we would also have to evaluate the plate itself, the connection plate, to see whether or not it would pass the bolt bearing check. And the other thing that we would need to do is we would need to check the weld capacity between the plate and the plate and the column, right? Because that plate is welded to that column using a fillet weld, probably using an E70 electrode. So we would need to know how long that weld is, capacity per inch times the number of inches. We'll talk about that later. But you can see how there's sort of like a hip bone connected to the leg bone kind of approach to get the load all the way to the ground. The very last thing that we would need to do is design the column to safely support the load, right? That's what we're going to do after connections, or after we get back to the spring brake. Does that make sense? Everybody okay with all this? Anybody have any questions about how we would approach this in the real world so far? Starting to see kind of like the big picture, hopefully. Okay. Now, what I want to do now is I want to focus on the riddle of a spliced connection. Okay. Now, a spliced connection is a little different than the connections we've been looking at so far. The connections that we've been looking at so far have really just meant to connect element A to a plate, right? Or element B to the next adjacent element. Instead, what we're doing here for a splice is essentially what happens when we have an element in a structure. Oh my goodness. Every time. Who is this? Oh, they're just going to have to wait. Sorry. I'll just say in class. This is what happens.
Take a little commercial break.
All right, break. So in the case of a spliced connection, so this happens all the time in structural elements that are very long. It happens in bridge land. Okay, let's just take the Nitro St. Albans Bridge as an example. How many there were on that site when we did the site tour? Those beams, they were long, weren't they? A little bit, right? It's not like it's, you know, the longest single plate girder span in the United States or anything. No, so it's a little long, right? I don't know, how many of you have ever driven in West Virginia before? Roads kind of do this, don't they? Right? It's not like driving in Iowa. So, let me ask you a question. How easy is it to transport a 562-foot long beam down the roads of West Virginia? Give them a point, right? We don't do that, right? Instead, what we do is we would ship that element in pieces and we would splice it together, right? So, what we would end up doing is something like this. So, it's the same element, but what we do is we have the element come in pieces and we splice it together. So, for example, we would put a plate on the top and bottom, and we would put bolts all the way through that. Now, I'll tell you that the spliced connection for beams, as opposed to the spliced connection I'm showing here, which is just for a tension member, is obviously a little bit more intricate. I've got moments, I've got shears, I have to splice the flange, I have to splice the web, I've got oodles of limit states I have to assess, I have eccentric loads, and there's a lot going on with a beam splice as opposed to what I've got going on here. But some of the ideas are kind of similar, so I kind of want to make sure that the thought makes sense. So let's just make sure we have an understanding of what's going on. So we've got member A and member B that are spliced here with these two plates that are sandwiched on the top and bottom. So this is kind of like the side view. This is the top view. So I don't know if it's coming through. I don't know if you can see on the screen. Can you see the dashed lines right here? You'll see that? So those dashed lines correspond to this gap in between the members, right? So if I was like looking above and I had like x-ray vision, I could see where the member ends and the member ends, and it would be those dashed lines. Does that make sense? Yes?
Why is there a gap in between them at all?
That's a good question. So it's typical to include a little bit of a gap for a few reasons, moisture drainage, you know, things like that. It's not totally necessary, but it's usually not a bad idea to have a little bit of a space there for workmanship. So just about every splice I've ever seen in practice has a little bit of a gap. When I say a little bit of a gap, we're talking about like half an inch, something like that. Nothing crazy. So that's a good question. So far, so good? Now, I want to go through the riddle of a splice connection. In other words, how do we actually assess its capacity, okay? Because this is, there's some thought that needs to go into this just to make sure that you're handling this appropriately, okay? So I have here that same splice connection, okay? And I want to make a very important, point about the analysis, okay? So, unlike the connections that we've looked at up until now, all of the bolts are all acting to transfer load in the same direction, right? We have a member connected to a plate or to another element and we yank on it. All of the bolts are resisting the load the same way, okay? That's not happening in a splice, okay? In a splice, we have a member and we're joining it and we're yanking on it. Half of those bolts are acting to transmit load to one side, to one member, and half of those bolts are acting to transmit load to the other member, right? Really, when you look at a splice, what you should be thinking about, instead of looking at this member as a whole, is recognizing the presence of symmetry, okay? Really what you should be doing, really what you should be doing is samurai sword or lightsaber through the member, okay? So really what we're dealing with is something like this. We have a plate transmitting load. Actually, let me make this a little bigger. I want this to be kind of really salient, okay? We have a plate transmitting load this way, And then we have two sort of cover plates or splice plates on top of that, transmitting load this way. All right. And if I go off of my diagram, so my diagram here, I have 1, 2, 3, 4, 5. Let's do that. So let's do 1, 2, 3, 4, and 5. And just to make this a little easier to digest, I'll fill these in. So these are the bolts from the side view. Okay. Now, just also to clarify what we've got going on here, let's put some dimensions on this. So what I'm going to call is this TM, and I'm going to say this is TM for the main plate, the main member. And what we'll do here is we'll say that this, we'll call this TS, or better yet, let's call it TS1, and let's call this TS2, okay? So in other words, this is the thickness of the main plate, and these are the thicknesses of the splice plate. Make sense so far? Okay. Now, I want to make some conclusions about bolt shear and bolt bearing. Let's start off with bolt shear, okay? Can somebody tell me a conclusion about looking at these bolts, just by eyeballing them, something that we're going to need to consider when we look up the capacity per bolt in 7.1? Like, let's assume you know they're A325. Let's assume you know they're 3/4 inch diameter bolts. When you see these bolts, what's the first thing that pops in your head?
Is it thread?
Not in the threads.
Double doubles.
They're in double shear. These bolts are in double shear, right? Because there's two shear planes that we have to fail through. So whenever you're dealing with a connection like this, the first thing to recognize, double shear. Okay? Right off the bat. The second thing I want you to think about is that we're only considering half of the bolts for connection capacity. In other words, like if I look at the connection as a whole, like the whole connection, right? How many bolts are in this splice? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20, 25, 30, 35, 40. There are a total of 40 bolts in the splice, but only half of them are transmitting load one way, and the other half are transmitting load the other way. So in terms of connection effectiveness, only 20 bolts are considered effective for the connection capacity. And if you're like, wait a minute, that doesn't make sense. There's 40 volts. How are you only counting 20? Well, let me ask it to you like this, okay? Here's the connection, right? Let's look at the connection. How many bolts would I have to shear in half or delete from this connection for it to no longer be effective in resisting load at all? And I posit to you the answer to that question is 20. Because if I were to take this splice connection and just delete all the bolts over here, is it doing anything? No, it's just, here's a member and it's not connected at all, right? So that's the amount of bolts I would need to delete for the connection to not be effective. So if I'm trying to ask what is the capacity of this connection, I don't account for 40, I only account for 20, right? Does that make sense? Okay, so that's usually something that's kind of hard to understand when you first start looking at splices. Like, why are you only considering half the bolts? Well, that's why, okay? With me so far? Okay. Now, before we start making conclusions, this pen sometimes. Before we start making conclusions about bolt bearing, okay, I want to go back to the formula for bolt bearing. Okay, so the formula for bolt bearing states that Rn is the minimum of 1.2 LCTFU and 2.4 dBTFU. And for this expression, we know that the hole diameter is the bolt diameter plus a 1/16 of an inch, and LCE is LE minus DH over 2, and LCI is S minus DH. Like, is everybody okay with that? Everybody's okay with that, right? So, here's what I want to isolate real quick. I would argue that if you want to compute bolt bearing capacity, if you want to compute capacity, okay, there are 4 variables that matter, okay? Well, actually 5, but I'm gonna make a point about that. So the 5th variable is the bolt diameter, right? But the 4 variables that really matter are S, T. Oh, sorry. Let me get back. S, L, E, T, and FU. Like with these 5 quantities, so with the bolt diameter, I can compute the hole diameter. With S and LE, I can compute these, and then I can take everything else and plug it into here. So those are the 5 variables that you need to compute bolt bearing capacity. Am I right? Okay. Now, do you remember how I said that whenever you're checking bolt bearing, there's always 2 cases. There's the part of the material that's transferring load one way, and then the part of the connection that's transferring the load the other way. Well, the same thing's true here. I propose that there are 2 cases for bolt bearing. The cases are, we'll call it case 1. Here, let me scroll down a little bit. Case 1, the main plate. And case 2 is the splice plate. And in case you had never seen that before, see how I did like the PL? It's almost like a center line symbol, like in CAD. That's shorthand for plate. Okay. So let's sort of look at this. Okay. One of the reasons that I said that this bolt diameter, I said there's 5 parameters, but that bolt diameter one doesn't matter. Why doesn't it matter? Well, if you're trying to compare capacity, right? The bolt diameter is the same for both the main plate and the splice plate, right? So we don't really need to worry about that, right? But each plate may have a different FU, right? Each plate might have a different thickness. So let's talk about thickness, okay? I propose that the thickness of the main plate is just going to be Tm. What about the thickness for the splice plate? I propose let's just add it up and use that value as the thickness in computing the capacity, right? What about the bolt spacing? Is the bolt spacing going to be the same for the edge plate and the main plate and the splice plate? Yeah, it's the same variable, right? So the only other thing to consider is maybe the edge distance. The edge distance might be different, right? Let's talk about that. So the edge distance for the main plate is going to be this distance right here. That's the edge distance for the main plate, right? Because those are the plates that are on the edge, right? But for the splice plates, it's going to be that distance right there. Right? And my drawing isn't very scaled because this looks like it's kind of different, although it would probably be the same. So. Make sense? Now the cool thing about bolt bearing is that sometimes you can look at it and see which one's going to govern. For example, if the main plate has a smaller thickness, a lower FU, and a smaller LE, why even bother checking the splice plates? You know the main plate's going to govern, right? But there are some instances where, like, the main plate may be thicker, but the splice plates might have a higher FU, in which case you kind of need to do both. You kind of need to check both. But fortunately, once you have all these parameters figured out, it's very plug and shut. Does that make sense? Okay. So the reason why all that's important is because when we start talking about this example that we're about to discuss, I don't think I'm going to do the entire example. Instead, what I want to do is I kind of want to just guide you through some of the decisions that you need to make in order to be able to do the example. The rest is very plug and chug grunt work, okay? So what I'm going to do is I'm going to take this example and I'm going to walk through the bolt shear, walk through the bolt bearing, but instead of doing all of it, I'll probably do some of it and just say, okay, if you do it right, here's the answer, and then let you sort of do that on your own because, again, this math is very mechanical. It's very rote, so you'll see what I mean. Okay. All right. Okay. So we have here a 1/2 inch thick member that is connected, that is spliced with 2 1/4 inch thick plates. So this is a 1/2 inch. These two are a 1/4 inch. Okay. We have 7/8 inch diameter bolts. All the steel is grade A36. So we're going to determine the design strength for the connection shown and determine if the connection meets layout requirements. Now, one thing I'll tell you we're not going to do together is check whether or not the connection meets layout requirements because I really think that's easy, right? Just check the minimum maximum bolt spacing, check the minimum maximum edge distance, see if these dimensions fall in between. That's not hard, right? The bolt spacing, so if you were checking minimum and maximum bolt spacing, let's just use our noggins here. Which one would you use? Would you use the 5 inches or the 2 3/4? Well, probably what I would do is check this against the minimum, probably check that against the maximum, right? Because I'm worried about this dimension getting too close together so the bolts don't knock into one another, and I'm worried about that dimension getting too far apart because I don't want water to seep in between the connection, right? So those are going to be sort of my key variables here. The edge distance, fortunately, the edge distance is 1.5 inches on every direction, so we don't really need to worry too much about that. Okay. So if we look at bolt shear, let's just list out the stuff we're going to need, okay? So help me out. Let's see. Bolt diameter, I know the bolt diameter is 7/8. Are we in Group A or Group B? Group A. Group A. All right. Threads included or threads excluded? I didn't tell you, did I? And if I didn't tell you, what do you do? Assume they're included. So we'll say Group A in. And maybe what I'll do is I'll put assumed for that. Single shear, double shear? Double shear. And how many bolts do I consider? 4, not 8, 4, right? Because half of the bolts are transmitting load to this member, half of them are transmitting to this member. So, do you all have enough right now to compute VRN for this connection as a whole? Capacity per bolt times the number of bolts. What's the capacity per bolt? Everybody brought their AISC 15th edition steel construction manual to do CE 414 structural steels at Commercial University.
48.7.
You got it. There you go. Okay, what's that?
48.7.
48.7 kips per bolt. 48.7 kips per bolt times 4 bolts is something like 194.8. Pretty easy, isn't it? See, one of the things about bolted connection analysis, the math is really easy. Like, it's really not hard. The difficult part is looking at a connection and making sure you know what you're looking up, making sure that you can identify what parameters are important. And so, like I said, like we've got this example, there's not really a lot that you need to do. You just need to say, okay, they're in double shear, they're 7/8 inch diameter, they're group A in, there's 4 of them. There you go. All right? Now, for bolt bearing, okay, and I'm going to try and summarize this in a way that makes sense. Okay. All right. So, first off, we know that the bolt diameter is 7/8 of an inch. So therefore, the hole diameter is that plus a 16th, not an eighth. And so we get 15/16. Okay? Now, in order to think this through, let's just recognize again that's sort of our governing expression. These are our starting equations that you might find on a formula sheet. Hopefully I'm not breaking up bad numbers. So, what I'm getting at though, again, is that T, S, LE, and FU are the key parameters. Okay? Those are what's important. So let's look at the main plate and let's look at the splice plates. All right? Let's start off with the FU. What is the FU for the main plate? What were we told about steel? What grade?
A36.
But what did it say? It didn't say just A36. What's the whole sentence say? All steel is grade A36. So, for this problem, for both the main plate and the splice plates, FU is 58 KSI. All right? Now let's make sure we're paying attention here. All right? What is the bolt spacing? Which bolt spacing value do we use? Do we use 5 inches or do we use 2 3/4? Well, which way are we yanking on the bolts? We're yanking this way, right? So we're talking, when we use these bolt spacing and edge distance values, we're talking about the ways that the bolts will tear through the plate. So which way are they going to tear through the plate? Are they going to tear through the plate up and down or left and right?
So the 2 3/4.
Exactly, the 2 3/4. That's the one that you use, right? But is that the same for both the main and the splice? Yes, it's the same, right? So S all right. What about LE? Is LE the same? This connection does not have a gap, by the way. So what is the distance from, if we're talking about the main plate, LE is this distance, right? What is this distance? 1.5 inches, right? What about for the splice plates? The splice plates, we're talking about that distance. What is that distance? 1.5 inches, right? Does everybody see that? So LE and finally, what about the thickness? What is the thickness of the main plate? 1/2 inch. What is the thickness that we're going to use for the splice plates? 1/2 inch, because there's 2 of them, right? 2 of them are 1/4 inch. So this is 1/2 inch. This is 2 times 1/4 inch. So what can I tell you about bolt bearing? There are 2 cases of bolt bearing, but for this problem, what can I say? They're going to have the same capacity. So just do one of them, right? So what do? So, we say compute LCE and LCI, okay? I'm going to tell you what they are. That's what they end up being, 0.594 and 0.938. The next thing that we're going to do is compute 1.2 LCE TFU, 1.2 LCI TFU, and 2.4 dBTFU. See, this is all very rote. I don't think we need to waste our time in class doing this. I'm just going to give you what these answers are. This one ends up being 20.66. This one ends up being 32.63. This one ends up being 60.9. Next thing we do is we compute, or maybe I should just say determine. RNE and RNI. RNE is going to be the minimum of the top and the bottom, which is 20.66. RNI is the minimum of the 2 lower ones. Then we determine or compute RN. For either of these, how many edge bolts do we have? How many interior bolts do we have?
2 and 2.
2 and 2. So RN so when you chunk that out, you get 106.58 kips, and finally compute phi RN, and phi RN is 79.93. And I'll tell you, that's the answer. Because it does, right? Because the bolt shear capacity was a lot less. So or a lot more, sorry. They were in double shear, you know, they were pretty hefty bolts, so. So yeah, so, make sense? Okay, now I'm gonna tell you something. You've got a connection homework. The two bolt bearing cases are not gonna be identical. Okay, so what's gonna have to happen is you're gonna have to do the math for case one and then do it for case two. But it's repetitive, right? It's just the same thing over and over again. It really shouldn't take that long. And you'll see like one of them's thicker, but one of them has a higher grade of steel. And the only way you're gonna assess it is just to be able to check both. The one thing I'll tell you is that the tension member is a W shape, so there are bolts on the top and the bottom. So make sure that you're being cognizant that you count for all of them. Also, make sure you pay attention to the detail because it may not be in double shear. But that's all I have. I will see you all on Monday. You all have a wonderful weekend. I will leave this up here if you want. Can we leave this up here for a sec? All right, let me stop my recording and then I'll hold it over in case I need it.